Hello, everyone. Yeah, have your attention, please. Thank you for staying late with us. And please make yourself comfortable. I think this is the first time I'm talking in a round table in your style. Please don't hurt your back and neck. Turn me in front of the screen, okay? My name is Guang. I'm Guang Hu from Microsoft, actually product manager. I'm also having joined with Joshua Zhang from our principal software engineering as well from Microsoft. So today we are trying to very excited to give you a presentation to sharing how are we going to pushing the boundary about the Kubernetes to the edge, and also the cost-sensitive kind of environment for the two-node Kubernetes. Here's today's agenda. So we are talking about why two-node actually matters, and how are we going to meet the customer requirement and resolve their problems. We are going to having recorded a demo because we have to working with the kind of physical server to represent you how the two-node Kubernetes working with a bare metal environment to see how the still can be reliable after one node is down, all right? And then Joshua will going through with us a deep dive into this kind of the design details. In the end, we want to having a discussion with you about the future plans, and also we're trying to maybe encourage all of you to helping us to shaping the future about the two nodes. In the narrative about the two-node kind of Kubernetes. Okay, let's get into some requirements. We know that if a customer today want to deploy kind of the bare metal Kubernetes cluster, also want to achieve highly available solutions, they have to making sure they have at least 3. We all know that about that. So I think the customer asking for less of that, I think also understandable. They want to saving the cost about the Kubernetes. And I can give you a very kind of good example. The customer actually having tens of the kind of thousands of the deployment in domestic and also in overseas. They have a retail kind of customer, retail stores. So their currently deployment actually involving 2 physical servers, 1 passive, 1 active, with the traditional applications running on the 2 servers, 1 active servers. So once the 1 server is down, active server is down, will fill back to the backup servers. I think this will be understandable for maybe legacy kind of architecture stuff, how it's running. But customers want to move into the Kubernetes. They want to leveraging the Kubernetes nature reliable solution to having the workload pod replacement, as well as they also want to having the great new feature of the Kubernetes, how it can be easily to deploy other solutions, storages, how to integrate with AI. I think we all go through all the kind of new features in today's earlier session as well. So customers want to moving to modernize this application according to their organization kind of strategies, but still they want to stick with that 2-node. They cannot tolerate about increasing more. You can imagine if their deployment is tens of thousands kind of deployment scale, massive scales. So I think we understanding the customer requirement about the costing, and then the layer down to they still want to smaller scale about the Kubernetes, but also want to having a high available kind of solution for them. So it's always, when we're talking about high available, it's always being between, the cost and also impact balancing stuff, right? So when we're talking with the customers, the customer also replies that they are actually altering different kind of scale to different kind of configurations. They also, even with using with 1 node for there's some very small kind of the grocery stores. So I think even with 1 node, they also need to considering how to maintain the services on that. For example, they can having some sort of other using the urban OEM partners to replacing the hardware even the hardware fails, and also to temporarily to temporary to moving to the other kind of the cloud services to expensive cloud services, temporarily hosting their services on the local. But all of these things is kind of balancing. But if they go to a very flagship or even bigger kind of the stores, they actually need to think about they cannot tolerate any time of the business going down. Like critical to the point of sales or other kind of printed services, they need to maintain there in the store, cannot, customer waiting in line, waiting for your return of your business. So that's something we are trying to deal to moving two requirements. One is the two-node, how we can resolving customers' cost-saving requirement, and also answer customer question, why I have to jump in from one node to three nodes to maintain the HA. How about I using two-node as well? So that's the the boundary about we are trying to talking about to pushing the customer forward to see how we can resolve this problem to the customers. If we understanding about this kind of nature of Kubernetes, I think the etcd play a very important role to keep the quorum about keep the current status running smoothly. And these things we need to keep a majority of the quorum very essential for maintaining the consensus for the Kubernetes etcd. So if we have a one node down, it means that we cannot make the majority. 50% is just a half and a half, right? So that's why we Kubernetes always have all the number of the requirement for the control planes, either 1 or 3 or 5. We cannot have a 2 or 4, right? So that's how they want to avoid this kind of the situations to meet the customer requirement. So that's some of the solution we're trying to introduce is about the storage witness to acting as a lightweight third-party, third voters during the cast deployment. So the design only extended, have the Raft algorithm in etcd, and also should be compatible with all these other Kubernetes toolings, and also as well as the Kubernetes other component as well. So it means that still can working together with the other your currently Kubernetes workloads without with the significant changes can working on the two node as well. So you can see if we have one physical or primary nodes down, the remaining nodes plus the storage witness still can keep the quorum in majority and moving things forward. So that's why we trying to introduce these things to our customer to see how we can helping them to meet their requirement and also resolve their problems. So we have a recorded demo. Hopefully we can play that in with sound. So the demo shows up the two physical machines with one machine down, how the application is still running normally, and how the control plane also running normally to helping the pods moving between the nodes. Okay, let's take a look at the demo.
In this demo, we'll showcase how our two-node Kubernetes cluster maintains high availability even when one node goes down, unlike the three-node requirement in standard Kubernetes today. We have two lightweight machines serving as Kubernetes nodes, both connected to the router. Additionally, a USB drive is connected to the router, acting as a shared storage witness for the two-node cluster. And we have a retail store app running on the cluster. In this app, customers can easily view products and add them to their carts. One day, an unexpected issue occurs on a node, causing it to shut down. To simulate this, we unplug the power of the top server. After that, the app continues to serve. Customers can still purchase items from the retail store. Our two-node cluster maintains high availability of the control plane even with one node down. This high availability ensures that the API server and control plane services remains operational. It makes the pods rescheduling possible to maintain application availability. Also, it allows us to check the workload pod status. Initially, the pod on the down node remains in a running status because the Kubernetes cluster has a time interval set to mark the pod as unhealthy. After about several minutes, which depends on the app configuration, the pod enters a terminating state, and a new pod is created on the live node. Thus, due to the high availability of the control plane, the pod is successfully rescheduled to the live node. Imagine the IT team receives a notification of the node failure via telemetry and then takes action to fix it. In this demo, we will simulate this by reconnecting the power to the server. Once the node is back online, the workload continues to serve without interruption. However, we notice that both pods are still running on node 1. If node 1 were to fail next time, both pods would fail, and the workload would be disrupted. This issue arises because Kubernetes lacks a mechanism to rebalance the workload. To address this, we can use an open-source tool called Descheduler. With Descheduler, we can see that the pods are rebalanced across the two nodes. This demo shows that two-node Kubernetes clusters can provide a highly available control plane and workload resiliency at a lower cost compared to three-node clusters. Thanks for watching.
Okay, thank you for the demo. I think that's something I also forgot to want to mention, the storage kind of the witness. Actually, when we say the lightweight, it also means a lot with not just the transaction, also with the size of the storage. So I think we can have different options. The storage has to be out of the field domain of the nodes. It has to be external storage. So we have a kind of small, as light as a kind of USB key connected to the router, just show as in the demo. And also, it can also be something highly available storage in the cloud. So that's something all optional can be achieved by this kind of storage witness to helping this kind of two-node Kubernetes solutions. So let me hand over to Joshua, go through very detailed about the design about this kind of problems. Thank you.
Thank you, Guang. Okay, so as Guang mentioned, our two-node solution is based on a modified version of etcd that runs a special extended Raft algorithm. We did not change any core etcd API like key value, list, watch, etc. The only thing we changed is in the class API. We add an optional flag to indicate if a member is a witness or not, and that's it. So because of this, the modified etcd stays fully compatible with the official version. And all the Kubernetes components like API server will just work without any change. So what does this mean for you? You can set up a two-node Kubernetes cluster using whatever tool you like and add a shared storage as witness member to the cluster to make it highly available. And the two-node cluster is resilient. It tolerates not only node failures, but also network partitions. And it does so without sacrificing any data consistency. As to the witness, it's super flexible. You can use the NF share or SMB share. You can use the cloud storage. You can even use a USB stick plug in the router, like we have shown in the demo. And when we talk about performance, it's also solid. The leader election time is about just a few milliseconds if you're using a local witness. And if you choose a cloud witness, the time will be like 500 milliseconds. So it really depends on the network. Now, you might be wondering if we really need a very powerful witness a powerful storage to serve as a witness, so it won't be the bottleneck of the cluster. Well, you don't need that. The witness will be touched only once for each failure occurrence or recovery. So in most of the time, for example, when all nodes are good, or even in a degrade mode, you have only one node up running, the witness will be idle, so it will not be touched. And the witness itself only needs like a few kilobytes of space to save its data, so speed and size don't matter here. So because of all this, we think this two-node solution will be a great fit for the edge scenario, and you will have a highly available two-node Kubernetes cluster that is consistent and performant, and most important of all, it works with all your existing tools. And the only thing you need to change, the only thing you need to do is to tweak your script a little bit to handle the witness, and that's it. So you might be wondering what this extended Raft algorithm actually looks like. But before we jump into that details, let's take a look at the Raft first, because extended Raft algorithm is based on Raft. You already know that Raft includes two major operations: a log replication that keeps data in sync across all nodes, and a log replication to keep data in sync across all nodes, and a leader election to pick the node with the most complete and consistent data. So we made some animation here to illustrate how this algorithm works and what's the difference between them. So let's take a look. So here is a leader. When it receives a record from the client, it will append the data to its own log and tagged with its current term number. And the leader will replicate the log to other nodes. And when the follower receives that log replication message, it will append the data to its own log, and the response client and the response the leader with acknowledgments. And when the leader receives quorum acknowledgments, it will commit this entry and respond success to the client. That's how log replication works. Now, besides the log replication message, leader also sends out heartbeats, just saying that, hey, I'm still alive. So when it goes down, some nodes will notice that and step up as a candidate and bump up its term number. Now, the candidate will send out vote requests to other nodes, and including its information of its last log entry. So all other nodes will know how up-to-date this candidate is, and they will vote these candidates if they think the candidate has as complete log as they have, and they do so by comparing the term and index of the last log entry. So here is how Raft algorithm works. And when the candidate finally receives quorum votes, it will become a new leader and start a new round of log replication and move things forward. Okay, now here is the extended Raft. As its name suggests, it's based on Raft, and we replace one of the nodes in the cluster with the witness storage, like W here. And we add two pieces of information to each leader, a replication set that is a subset of the nodes and the witness that the leader will replicate its log. And the size is the number of the nodes here. And also a subterm number that uniquely identifies a replication set within a term. So when everything is good, a replication set will just be nodes, but no witness. So the replication only happens between these nodes. Like what we have in a Raft, when the leader receives the record, appends data to its log, and now it tags both term and subterm to it. And same as that in Raft, it replicates the log to other nodes, gets acknowledgments from them, and commit it if they had enough acknowledgments here. Now, things got a little bit different here if a node follower goes down. Now, leader will know that, and will exclude this broken node from the replication set, and add the witness into it. Now, the replication set changed from AB to AW, and also the subterm number is bumped up because it's identified, uniquely identified as a replication set. Now, besides the log replication between nodes, leader also needs to replicate its data to the witness. And it does so by pick up the record with the quorum minus one acknowledgement. That means it needs one extra acknowledgement to commit this entry. And it will write the term, subterm, any replication set to the witness. The success of this writing will be considered as acknowledgement from the witness. And as that in the Raft, the leader will commit it upon quorum acknowledgements. So far, it's very similar to that in the Raft. Now here comes the fun part. From this time on, for all the records of the same subterm, the leader will no longer need to talk to witness. So take example here, the leader will get the records here, append to his own log, and commit it immediately. We call this a shortcut replication, and this is how extended Raft algorithm cuts down the times we have to talk to the witness. Now, in leader election, like the log replication, the leader election behaves very similar to that in the Raft. The voting rules between nodes are exactly the same as that in Raft. But here, we know that the witness do not have the index. It only has term, subterm, and the replicate set. So the voting rule for witness will be a little bit different. For most of the time, witness can use term and subterm of it, the last log entry, just like a term and index for any other node. So like here, the candidate have his last entry, a term and the subterm 1, 1, and the witness has 1, 2. So it will reject the votes for the candidate. But there is a special case when the candidate and witness have same term and subterm. In that case, we need an actual check to ensure that the candidate can become a leader if and only if it gets all its votes from the consent of this witness. So this is how extended Raft algorithm work. We know that the correctness of this algorithm is crucial to know the Kubernetes cluster. So we conduct a formal proof to prove the correctness of this algorithm in theory. And we have leveraged the TLA plus modeling to verify the algorithm's correctness. And we also set up a two-node Kubernetes cluster and really measure its availability and compare to a three-node cluster. So let's take a look. Okay, here we set up two clusters. One is two-node clusters with a modified etcd. Another is a three-node cluster with official etcd. We have test load running in both clusters, and the pod just simply echo back the request from the client. And we also have the test client to keep adding, deleting, and updating Kubernetes resources using kube control command. And we randomly apply node failures and network partition failures to these two clusters. And finally, we collect all the available data and come up with these 4 charts. On the left side, you will see that the workload availability and control plane availability for the 2 nodes. And on the right side are 3 nodes. The gray bar here indicates a node down time slot when the node is down. And the red one is when network partition happens. So we can see that the 2 clusters have almost 100% availability, control plane availability, and they have comparable workload availability. Actually, most of the time, they have 100% here, and only some jobs happen at the beginning of each fault, which is expected because these are from the requests that were sent to the node that were brought down or isolated by the network faults. So with this result, we feel confident to say that the 2-node Kubernetes cluster is equivalent in the resiliency and the performance comparing to a 3-node cluster. Thank you.
Yeah, thank you, Joshua. So very comprehensive kind of explains. And also, so I think that let's recap. We are introducing a very lightweight story witness to helping customers resolving the two nodes, the native quorum issue. And then, so when we asking this kind of customer requirement, I think we also see it can be common. And also, we are working very closely with the community to move this feature upstreaming, to making sure we can have officially kind of the etcd official feature in the future, to see how we can having this one also everybody can use that, to see to rebuilding your all solutions to the customer. And also, I think that's I think that when we're talking about two-node Kubernetes solutions, we're not just about the etcd, not just about the control planes. It is very important, but also rely on whole ecosystems to working on how we can support the two-node solutions with the applications, the best practice about operations of failover, as well as a very key, very important, like I like talking with someone in this room about the storage, how we can providing the storages to support the two-node solutions. I think all these things will be very interesting to continue with you, engage with you folks. And also, I have a link here so to join us in the discussion, to share your comments, your feedback, as well your questions. So we're all welcomes. So please let us know how you think about the two-node stuff, and then share your ideas with us. All right. So last one is a Q&A, and also we have a code scanned with us. You want to continue with the discussion with me, and also with our teams, and also we have a bunch of other folks. So happy to talk with you if there are any question or any kind of engagement possible we can have in working together. So yeah, let's see if we have some question. Sorry. Thank you.
So in the CAPI theorem, you have to compromise at least one of consistency, availability, or partition tolerance. So my question is, which one of them is compromised in the two-node Kubernetes?
I'm not quite sure I can answer clearly the question.
The CAPI theorem asserts that you can't achieve consistency and availability and partition tolerance. You can achieve all three of them. So you have to compromise at least one of the three C, A, and P. So which one of them is compromised?
So I think currently maybe let me try to answer your question. Maybe let's see how it goes. So we having, as you mentioned, that we need to making sure that one of the copy is get into the witness storage, right? So we are trying to. Because we are trying to making sure the customer can achieve that kind of two-node kind of Kubernetes availability and same level of the three nodes. But I think you're right. For example, I think we can only talk about one node down, right? So we also have other cases. But I'm not quite sure if you're thinking about the availability of overall systems is compromised. But I think that's also we are thinking about is still the same, even with one copy of the storage. But we still keep a corner about the other kind of representing another kind of nodes to see how we can achieve in the same level of the availability stuff. I'm not quite sure if I answer questions. Maybe we can follow up offline if you want to continue stuff. Okay.
I couldn't catch up the algorithm detail. But what was the requirement of witness node? So as Suda-san asked, so some failure happened. Witness must have ability to access the actual data or something, right? So what was the requirement of witness must have?
Okay. So I think the witness is something that's just a storage, right? The storage means that they have not something running on that. So it means that the nodes, the other two etcd pods need to handling, as just Joshua mentioned, the algorithm that they need to handling the data to consistent between the witness and also the primary running nodes. So the story itself do not have any kind of capability to do anything. It's just a copy, one copy of this kind of data, and then to making sure the etcd itself can consume the data to making sure the data is also consistent between other two copies on that.
Okay. Yeah, thank you.
John discussion with us. We can definitely follow up with you more
I need to
about
deep
the
inside.
algorithm.
Yeah.
Okay?
Thank you.
No problem. Any question?
Thanks for the presentation. I'm Hiroki from HA Corporation. So I'm curious about how many lines of code Kubernetes you updated to support this two-node cluster. So is there any difference in the Kubernetes implementation itself? Is there a difference, or only etcd node? Or I'm curious about the difference, code level difference.
Okay. I think the maybe quick question will be still the same etcd pods we are going to maintain, but I maybe leave the question to Joshua.
Yeah, actually we only modify the etcd to make it run with the extended Raft algorithm. And but if you are setting up the two-node Kubernetes cluster, your tool may have some restrictions. For example, class API, it does not support the even number of control plane. You need to tweak it a little bit to make it happen. But other than that, you can just use the modified etcd to make it work. If you're using kubeadm, it just works without any change.
I see. So there is no rebuild for the Kube API server and the Kube scheduler or something like that?
No, just change the image and that's it.
Okay, that's interesting. Thank you.
Thank you.
Thank you. Thank you for the question. This one, please.
Thank you for the interesting session. I understand the witness is the shared storage between each etcd node. Is it right?
Yeah. Yes.
Yeah, thank you.
Any questions? Okay, great. So if no question, please scan the code. Get engaged with us so we can follow up with that to see if you have any further stuff want to share with us. Thank you very much, and so enjoy the rest of the event and also enjoy the welcome reception. Thank you.